Okay, so now we are going to start talking about propositions and truth values. Okay, so what we're going to be dealing with in this video is now going on to more definitions, and we're going to talk about what are propositions and what are truth values and what are some of the tools that we use to determine the truth value of a particular proposition or even a combination of propositions as we go forward. Okay, so let's jump right in. So we always start with definitions. It's always good to start with definitions here. So first definition is a proposition. So basically a proposition is a statement that is either true or false, but can't be both. Okay, so anything that we say or state or claim um, that is can be either true or false, but not both, is by definition a proposition. Okay, so what are not propositions? Well, things that are not propositions are things like commands, right? Shut the door, um, get me a cup of coffee, please. Um, Questions are not propositions, right? So if I say, hey, what's the weather like today? That is not a proposition. So propositions in English or any language is going to be a declarative statement, right? A declarative statement. It declares something. It makes a statement. Okay. Um, what other? Oh, exclamations are not obviously are not propositions either, right? If I say wow or fantastic, right? Those are not propositions. Also, if I say, um, oh, what can I say? If I say, um, oh, if I say Abraham Lincoln was the greatest president um, that there ever was, that is not a proposition because, see, that may be true or false to me, but it is people might disagree with that, right? So that's an opinion, right? So opinions are not propositions because they can be true or false given the audience, right? True and false at the same time. So we got to be careful about how we say something, or not. Well, let me take that back. It's not how we say something. It's just we got to be uh, aware of what sentences are and whether they're true or false in an objective way. What would also be, um, let me see here. Well, we'll get more into it. Okay, now, whenever we look at propositions, we always want to see whether they're true or false, and we typically mark them with either two letters, T or F, right? T for true and F for false, just to keep things simple, right? And we're going to get more and more in symbolism because, again, as we get more complicated sentences, more complicated propositions, we're going to want to use symbolism to make things a lot easier to read and easier and quicker to write. So more concise, um, and so that's going to be our go-to. And one of the tools that we're going to be using is a truth table. So a truth table is a great tool used to figure out when a statement or combination of statements is true or false and under what situations they are true and false. So with this tool, it will take the guesswork out of figuring it out. Okay. Negation or opposites, right? So a negation of a proposition just means the opposite truth value. So if I take a proposition P, now P is the symbol for some proposition, right? So P could represent the statement the shirt is yellow, right? So it just represents some logical statement that we're making, some proposition. Um, Now, if I want the negation of the proposition, I'm basically taking the opposite truth value. And we say that so instead of P, we would say not P. Okay. And so in this case, here's an example of a truth table. And so we see here that under this truth table, okay, notice that we have two columns. We always start with what's given. So P, right? So P can either be true or false, right? We don't know the whole purpose of the truth table is to figure out all the possible conditions when a statement is true and false. So if we start with the proposition P, right, one proposition, then we're only going to have two values, either true or false, T or F. Now, if we make the next column, then we say not P. Well, if P is true, then not P would be false. And if P is false, then not P would be true. That's how negation works. Okay. Now the symbol for not P, or the negation, we wouldn't use not. We would not write not. We would use the symbol, the tilde. So we would say tilde P for not P. We wouldn't use the word not. Okay. So get used to writing the tilde with the P for a negation. Okay. We'll do more. So let's use this example here. It says, find the negation of the proposition, Amanda is the fastest runner on the team. So we want the opposite truth value. So if we look at, so before we get into the symbols, let's just think about this. And some of this might be easy, and we're going to start easy, but it will get faster, or excuse me, it will get more complicated. So find the negation of the proposition, Amanda is the fastest runner on the team. So there's a couple of ways we could say this in English, right? We could say, well, okay, what's the opposite of that? Okay, if we say Amanda is the fastest runner on the team, well, then we could say Amanda is not the fastest runner on the team, right? We could say it that way. Or we could say, hey, it's not the case that Amanda is the fastest runner on the team. Or it's not true that Amanda is the fastest runner on their team. Right? So there's many different ways we can say the same thing in English, right? Which makes it, when it comes to reasoning and logic, it makes it complicated, okay? Because there's so many different ways of saying the same thing, right? And we'll get more into logical equivalence later on, but let's stick with this. Okay, so now, so when we want, if Amanda is the fastest runner on the team, and that is a true statement, and we want to make the opposite, okay? So let's say this. First of all, let's say P. Let's define P, right? So let's get into how we would do this. We would first write this symbolically to make it easier to write, okay? So P would represent the statement, Amanda is the fastest fastest runner on the team, right? Okay, and so if we make our value, right? So let's just get into, so here's P, so we put TF, and then not P would be FT. Okay, so again, just a little example of how we would write this symbolically. Okay, again, the main thing is first we got to define what our proposition is, right? So we got to translate our English statement into a symbol. Okay, so now, so again, so that's a couple of different ways we could say that, right? So right, so we just, okay, so we already did this. Okay, now, what about a double negation? You know, not P. So we start with the proposition P, and we did not P. Okay, so again, we would not write the two words not. We would write tilde P. Okay, now, the cool thing is negations in logic are like negative signs in mathematics, right? They cancel each other out. Every pair of negations cancel each other out. So not P is the same as P. Okay, so again, if we just use our truth table, right, it makes it really easy. So we start with P, and then we have not P, and we have not P. Okay, so again, what are the possible truth values for P? True and false. And so now from there, we could just fill out the rest of the table. So not P would be the opposite of P, so that would be FT, and then of course not P would be the opposite of negation. So basically I'm taking the negation of not the negation of P. So now I'm going to take the opposite of the second column. So, which brings me back to the first column. So notice that these two have the same truth values. Okay, so P and not P both have the same truth values going down the columns. Okay, so that is how a double negation works. Okay, so here's another one. So, and again, in English, we avoid double negatives, right? We always avoid double negatives. We would never say it's, not raining. Okay, but it does come up. So in this case here, now, by the way, just again, English is a complicated language, and again, there's many different ways of saying something, so we've got to read things carefully. Okay, this is where critical thinking comes in. It says, after reviewing data showing an association between low-level radiation and cancer among older workers at the Oak Ridge National Laboratory, a health scientist from the University of North Carolina, Chapel Hill, was asked about the possibility of a similar association among younger workers at another national laboratory. Okay, so here's what he said. He was quoted as saying from the Boulder Daily Camera, "My opinion is that it is unlikely that there is no association. Does the scientist think there is an association between low-level radiation and cancer among younger workers?" So here's our proposition. My opinion is that it's unlikely that there is no association. So here's where we have to kind of, again, critically think and look at the words unlikely and no. So unlikely, so again, when we're talking about probabilities, when we say something is unlikely, we're saying that there's a low probability of something occurring, or a low probability that something is true, or something right, of something happening. So unlikely would translate into a negation, into a no or a not. Okay, so in this case we've got two nots. So he's saying it's unlikely that there's no association. So if he's saying that it's unlikely that there is no association, then what he's also saying is that there's likely there is an association. Okay? Which is, these are two negatives. So what he's saying is that in his opinion, there likely is an association. Okay? Or simply, you could just say that he believes that there is an association, or likely that there is association. Okay? So there's the double negative, right? So here's the solution, right? So now if we take our statement, right, it's likely that there is an association between low-level radiation and cancer, right? So P is, and again, by the way, we always look at P in the positive sense, right? So we don't put any negatives in here. So we wouldn't define P as it's unlikely that there is no association, okay? So whenever we translate something into symbolism, we're always doing it from the positive. Is that the best way of saying it? We want to put it in the simplest form, if that makes sense. Okay, so any negations we want to avoid, we want to leave out. Okay, so in this case here, P is simply, it's likely that there is an association. Okay. So again, the word unlikely gives the statement basically a not, right? And then of course, no is the same as not, right? No association. Okay, so because the double negation has the same truth values as the original proposition, we can conclude that the scientist believes that it likely that there is an association between low-level radiation and cancer among younger workers. All right, now let's talk about logical connectors. Now here's where we're going to throw one more thing into it. We're going to build off of what we just said. So now let's use multiple statements, okay, multiple propositions. So logical connectors. Well, the three logical connectors we're going to focus on are the words and, or, and the conditional if then. Okay, and, or, if then. Okay, so we're going to use an example of two propositions. So let's say we have these two propositions. P represents I won the game, and Q represents the statement it was fun, right? So let's look at these three connectors. So let's look at and. Okay, so if we use and with these two propositions, and we get a new proposition, I won the game and it was fun. So that's a completely new proposition now, right? So we took two propositions, connected them by the logical connector and we came up with a new proposition. Or, if we use or, we'll come up with this new proposition. I won the game or it was fun. And then finally with the conditional if then, I would come up with something like this. If I won the game, then it was fun. So those are new propositions that we have to consider the truth value of, right? When are they true? When are they not true? Okay, now, and statements. Now, and statements in logic are called conjunctive statements, okay? The and is called a conjunction. Now, in English, and, or, but, yet, those are all considered conjunctions, right? They connect sentences together. But in logic, we call and is a conjunction, right? And so in logic, and is the only conjunction, okay? So now the way this works with and is, I'm gonna do this in a couple of different, in one way that is really helpful. Look at and. Whenever you look at logical statements, you always want to ask yourself, when can somebody say I lied? Okay? With conjunctive statements involving and, both component propositions, the P and the Q, must be true in order for the conjunctive statement to be true. Okay? If either one or both of the composite propositions or component propositions are false, then the whole thing is false, because, and we'll do an example. Okay, so notice here that we've got our truth table. Now notice that all we're doing is, again, we start with the first two columns in this case because we got two propositions, P and Q. And so now what we need to do is we start by writing out all of the possible truth value combinations, right? So one combination is that both can be true. Another combination is that P is true and Q is false, or P could be false and Q is true, or they both could be false. Those are the only four possible combinations of truth values. Okay, so that we always start with that, okay? And so now from there, we put our and. Now notice that the symbol for and is the caret. So we would never write and, we would just put the symbol caret between them, okay? So that would be P and Q. Now, notice how the only row where P and Q are true is the first one. Okay? Otherwise, it's false, because again, in order for an and statement to be true, both component statements must be true. Okay? So here's an example. says evaluate the truth value for the following two statements. A, the capital of France is Paris and Antarctica is cold. Okay. Now, here's the thing. We want to evaluate the truth value of this, right? So let's use, okay, the capital of France is Paris. Let's call that P. Here's our and then the other statement is Antarctica is cold. Okay. Now, are they both true? Is the capital of France Paris? Yes. So one way we could do this is we could just put a T. Right? So we could do P and Q, which translates T, and Q is also true, T, so it's T and T, and since they're both true, we know the whole statement is true. Or we could do it using the truth table. Oops. PQ, T, oops. Okay. P and Q. So this would be true because they're both T's. The rest are going to be false because there's at least one false, right? So again, always ask yourself, when can you be called a liar? And with and statements, you can be called a liar if at least one of the two things you said is false. Okay, so A is a true statement. What about B? B says the capital of France is Paris and the capital of America is Madrid. Well, we know that this statement here is true. Oops. There we go. And there's our and then of course the capital of America is not Madrid. So that's a false statement. And so therefore, the whole thing, and I'm going to put it above the and, is false. Okay. And notice how I wrote the truth values underneath the and statement, the and symbol. Okay. Again, just a little best practice when it comes to truth tables. Okay. All right, now, or. Now there are two different ors that we have to consider. One is an inclusive or, which means either or both, right? So it includes the possibility of both being true. Then there's an exclusive or, which means it's one or the other, but you can't have both. Okay, right. Now what's the difference? Inclusive or would be, would you like if it allows for the option of having both, would be an inclusive or. Okay, like would you like to buy the red shirt or the white shirt? And the customer says, well, I'll take both. Okay, and the customer says, oh sure. Right? So inclusive or was meant there. But if you're at a restaurant and the menu says it comes with your choice of salad or soup, right, with your meal, and the patron says, I'll take both. Well, you can't get both because it's implied that it's exclusive. You get one or the other, right? And assuming that you're not paying for them, right? Okay. that it's included in the meal. One of them is included in the price of the meal, right? So you either get a super salad, right? So typically we understand in the context that that's an exclusive or. It's one or the other, but you can't have both, right? So that's the difference. So now in logic, we always assume that it's inclusive, right? So in logic, the or is always assumed to be inclusive unless it states otherwise. So now let's look at the terminology here. So again, and was called a conjunctive statement. Like, so an and statement is a conjunctive statement. So and is called the conjunction. But if it's an or is a disjunction. So any statement that's connected by or would be a disjunctive statement, okay? And here's how we do the truth table, right? So again, we start with our 4 possible combinations because there's 2 truth values that are being connected. So again, it's T, 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 F, F, T, or F, F, right? So again, you'll start to realize the pattern as we get more and more, okay? With 1 truth value, or excuse me, with 1 proposition, we only have 2 rows. With 2 propositions, we end up with 4 rows. If we add a 3rd proposition, by the way, we'll end up with doubling the number of rows, which then it'll become 8 propositions, okay? And there's a pattern to showing it. Notice how, in this case here, we've got 2 F's followed by 2 T's. So half of the rows are T's and half the rows are F's. And then it breaks down to half of that in the next column. So half of these are T's and F's, and then half of these 2 rows are T's and F's. Okay, that'll give you an idea of the pattern that we use, or that I use, to write out all the possible truth values, regardless of how many propositions we're connecting. Okay, now the symbol for or is the V, right? So it's the opposite of what the and was, right? So the and was the caret, and so the symbol for or is the flip of it, right? So instead of or, we wouldn't write or, we would just write the little v. Okay. Now notice here that the truth values for the disjunctive statement are like the opposite of the conjunctive statement, the and statement, right? So the only way you can call me a liar if I say an or statement is if I don't do, or if both of the things I said don't happen, right? So otherwise, I told the truth, right? So if I say I'm going to go to the movies or I'm going to hang out with my friends, as long as I do at least one of those 2 things, you can't say I lied. The only time you can say I lied is if I don't do either one of those things. Okay? And that's the way it works. Okay? So, and statements are only true if both of the component statements are true. Or statements are only false if both of the statements making it up are false. That's the way it works. Okay, so here's the situation. Consider the statement, airplanes can fly or cows can read. Is it true? So we've got our statement, our proposition, airplanes can fly, we'll call that P. Here's our or statement, we'll use the symbol. And then cows can read would be, make that our Q statement, Q proposition, okay? And so again, when is a or statement false? Only when both of the components propositions are false. And so in this case, airplanes can fly is true. So we know it doesn't matter what the other one is, whether it's true or false. As long as at least one of the 2 statements is true, the whole thing is true. So this would be a true statement, even though cows cannot read. It would still be a true statement. Okay, now, conditional propositions or implications, if-then statements. This one tricks students, okay? The only way an implication is false is if you have the if part of the statement is true, but the then part of the statement is false. So here's the form. Now, typically the way we write this, we would write this P with an arrow Q, or this arrow implies, right? So P implies Q is another way of writing it. So symbolically, we would use the arrow, okay? This would be the if part. This would be the then part, okay? We call P another, just so you know, the P would also be called the antecedent, okay? So what comes before the arrow is the antecedent. What comes after the arrow, we would call that the consequent or the conclusion. So also P is also can be called the hypothesis, right? But more typically, it's the antecedent followed by the consequent. Okay, so now let's look at the truth table here. So again, we've got our first two rows, always the same. And then of course, the only one that's false is this row here where we have a T followed by an F. So T followed by an F will give us a false statement. Otherwise, the statement is true. Okay, so let's use an example here. So think about this. Let's say I tell my son the day of a spelling test, and I say, okay, if you get 100% in your spelling test, I'll take you out for ice cream. So what are the possible outcomes of that? Well, let's say my son comes home and he gets 100% on his spelling test, and I take him out for ice cream. Can you say that I lied to him? No, of course not, because I did what I said I was going to do. He got 100% on his spelling test. I was obligated to take him out for ice cream. That's what I promised. That's what I said would happen. Okay. Now, what if he comes home and gets 100% on his spelling test, and I don't take him out for ice cream? And I say, no, sorry, changed my mind. Well, now you can say that I lied, right? Because and that should be obvious, right? I said I would take him out for ice cream if he got 100% on his test. He came home, he got 100% on his test, and I didn't take him out for ice cream. He would have the right to call me a liar. Okay? Now, where it gets confusing for students are when it comes to the other possible outcomes. What if he came home and he didn't get 100% on his spelling test? He got a 95. And I tell him, hey, son, let's go out for ice cream. So I take him out for ice cream anyway. Did I lie? And the answer is no. I did not lie to my son. Why? Because I was only held to my promise if he got 100%. I just told him what I would do if he got 100% on a spelling test. I didn't say anything about what I would do or would not do if he didn't get 100% on a spelling test. All I said was, okay, here's what's going to happen. Here's what I promise to do if you get 100% on your spelling test. If he doesn't get 100% on his spelling test, all bets are off. I can choose to take him out for ice cream anyway, or I can choose not to. In either one of those cases, you cannot tell me that I lied to my son. Because all I told my son was what would happen if he got 100% on his spelling test. Okay? That's why the only time you can say that the statement is false is if the antecedent is true the if part, and the consequent is false, the then part. Okay, and then of course, again, they use hypothesis and conclusion. That's fine. Typically, we also use antecedent and consequent. Okay, same thing. Okay, so now here's where it gets interesting. The following are common alternative ways of stating an implication. If P, then Q. So now you've got to recognize these. Some of these you've probably seen most of these. Some of them you haven't. Okay, but these are all the ways that we can commonly use in English to say the same thing, to say a conditional. Okay, P is sufficient for Q. Okay, that one you probably haven't seen before. So we would say P is a sufficient condition for Q. Okay, so P implies Q. Another way of thinking about this is think of the word sun, but written like this. So we've got this like sideways U, right? So that's another symbol for implication. So S implies N. We'll get to the S and N. But S represents sufficient. So whatever comes before the implication, we would always say is the sufficient condition. Okay, just so you guys know. P will lead to Q. Okay, that's another way to say the same thing. If P, then Q. P implies Q. I said that earlier, so that's another way. Q is necessary for P. There's the N, necessary. Okay, and sufficient. Okay, so P is the sufficient condition, Q is the necessary condition. Okay, there's a difference. Oh, we can change things around. We could say Q if P. If P, Q, Q if P. Same thing. Q whenever P. Okay, so now let's talk about variations of the conditional. Okay, now you're going to have to be responsible for knowing these. There are 3 different variations of writing the conditional. They're different statements that we want to make sure we understand. So let's say we start with a conditional, if P then Q. You know, P and Q can be anything. And let's call this, if it is raining, then I will bring an umbrella to work. So what is P? P is the statement, it is raining. The if is not part of that. And then the Q is, I will bring an umbrella to work. Okay. So the converse of a conditional statement is just the not the opposite, but it goes the opposite direction. Okay. So if P then Q, the converse goes the other way. So again, think about the symbolism. P implies Q. The converse would be just what? Q implies P. So you're flipping the arrow. Okay. So what does that mean? The converse of the statement would be what? If I bring an umbrella to work, then it must be raining. Okay, so that's the converse. The next one is the inverse. The inverse is all I'm going to do is negate both sides. So I start with my conditional. To get to the inverse, all I'm going to do is negate both sides. So it'd be not P implies not Q. That's all I'm going to do. So that's the inverse. So what does that mean? It means that if it is not raining, then I will not bring an umbrella to work. If it is not raining, then I will not bring an umbrella to work. That's the inverse of the original conditional. And then the final one is called the contrapositive. And this basically does the converse and the inverse all in one step. Okay? So we're going to flip the arrow and negate both sides. So we get not Q implies not P. And that's the contrapositive, which means, what am I saying? I'm going to say, if I do not bring an umbrella to work, then it must not be raining. Okay? And that's it. So make sure you know how to write these in English and also write them symbolically. Okay, now, logical equivalence. What does it mean to be logically equivalent? It means that they have the same truth values in the truth table. Okay, so if you look at a truth table for two logical statements, if they have the same truth values going down the table, going down the columns, and they match all the way down, then they are what we call logically equivalent. They are basically saying the same thing. Okay, so if we look at this truth table, so look at this truth table consists of all of the conditional and all of the variations. Now notice again, we start our truth table with all of the possible combinations of P and Q, and then we build our truth table bit by bit, right? We don't just go right to the end. So what are the first things we want to do? Well, in this case, some of these conditionals involve not P, and some of them involve not Q. So we want to add the columns for not P and not Q, right? So that's going to be important. And then now we're going to write out our conditional. Okay, so here's our conditional. And again, we look at all the truth values. So again, TT is going to be true. And then again, it's only false if it has a T followed by an F. So this is going to be false. And then the rest are true. Okay, now, again, this is a conditional. The next one is a conditional, but it's if Q then P. So Q is the first one. So we have to go kind of read it backwards, right? So now we're looking for a T followed by an F, but Q is first. So we're going this way. So, and here we go, right here. So we have a T followed by an F. And so this is the only one that's false. Okay, same thing here. If not P, then not Q. Now we're looking at these two columns, right? So not P is first. So again, so we're looking for an F followed by a T right here. Oh, I'm sorry. T followed by an F. I forgot. We're looking at not. That's wrong. So a T followed by an F, which is right here. Sorry about that. So T followed by an F right there. And then finally, we have not Q followed by not P. So now we're going to go this way because, again, not Q is first. So we're looking for a T followed by F going the other way. So that would be this one, the one I was originally said. So we have a T followed by an F, and look at that. It's the only F. Okay. Now, notice that this column and this column, right? So the conditional, P implies Q, and the contrapositive, not Q implies not P, all have the same truth values going down the table in the same order. Those two are logically equivalent then. And also, by the way, look at these two. The converse and the inverse. They also have the same truth values going down the table. Those are logically equivalent statements. Okay, so now we have two, oops, that's wrong. Those two. All right. So consider the true statement: if a creature is a whale, then it is a mammal. Write its converse, inverse, and contrapositive. Evaluate the truth of each statement. Which statements are logically equivalent? Well, we already know which ones are going to be logically equivalent, but let's go ahead and do it anyway. Okay? So again, we're going to write the symbolism, right? Always write the symbolism, make things easy on yourself. So we're going to take the two statements. A creature is a whale, right? That's going to be P, and then it is a mammal, or the creature is a mammal, however you want to say it, is our Q. Okay? So the converse would be going the opposite direction. So it would be, if a creature is a male, then it is a whale. If a creature is a mammal, then it is a whale. Now, obviously, if you think about it, we know that that is a false statement, because there are lots of males, or excuse me, there are lots of mammals that are not whales. We can name lots of them. Inverse. Okay, so now not P implies not Q. So that's going to be the negation of both sides. So that would be, if a creature is not a whale, then it is not a mammal. And that statement is also false, because again, we can come up with examples, counterexamples that show that that's not always the case, right? Dogs are not whales, but they are indeed mammals. There's your counterexample that shows that that is a false statement. And then finally, the contrapositive. If not Q, then not P, or not Q implies not P. If a creature is not a mammal, then it is not a whale. And that is absolutely true. That is the same thing as the first statement, right? So if a mammal, if a creature is a whale, then it is a mammal. That is true by definition of a whale. It is also true, and the same thing, that if a creature is not a mammal, then it cannot be a whale. Okay? Because we know that all whales are mammals. And again, note that the original proposition and its contrapositive have the same truth values and are logically equivalent, and also similarly with the converse and inverse, as we just saw in the previous slides. All right, there we go. So that finishes up logical propositions. And truth values and truth tables. There'll be more to come, so we're going to have a lot of fun with this, but stay tuned until next time. Have a great day.